You with the ions. So far, the first three categories of anions. What were they again? The nitrates, chlorates, acetates, the chlorides, bromides and iodides, and the sulfates. For the most part, those are soluble. And so the first three categories of anions mostly are soluble. The next three categories of anions are mostly insoluble. And so we're on A, B, C, D, E. We're on E. And so the first one we're going to look at are hydroxides. What is hydroxide, the ion?
H minus.
Hydride is H minus. Very close. Hydride is H minus. Hydroxide is OH minus. So we're looking for this, compounds that contain this anion. These are mostly insoluble. So now we're switching from soluble to insoluble. Mostly insoluble except for group 1, ammonium. Well, if it's group 1 or ammonium, we wouldn't have gotten this far because we would have stopped at step A. Not have come this far, but just for thoroughness, we'll put those in. Group 1, ammonium, and calcium, strontium, and barium hydroxide. So when hydroxide is paired with one of those, it's soluble. And so let's look at one of these. How about barium hydroxide? What's the formula for barium hydroxide? BaOH2. Is it soluble or insoluble? Barium hydroxide, solid barium hydroxide is white solid. It is insoluble. Oh, wait a minute. Did I get that right? Except, these are mostly insoluble except these, which would be soluble. And so barium hydroxide is actually soluble. Like this. How about this? AlOH3. What's this called? Yeah, aluminum hydroxide, right? Aluminum hydroxide, is it soluble or insoluble? Aluminum hydroxide is insoluble. So it's not one of the exceptions, therefore it's going to be insoluble. The exceptions being these here. Next one, this is a very common hydroxide, maybe the most common hydroxide you'll encounter, and that is sodium hydroxide. What is the formula for sodium hydroxide? NaOH. Sodium hydroxide has other names. It's also called drain cleaner or lye. That's sodium hydroxide. We have this one, ferrous hydroxide. Ferrous hydroxide, this is kind of an awkward name. Probably be more appropriate to call it by its modern name, which would be iron 2 hydroxide. Iron 2 hydroxide has a formula of what? FeOH2. Is it soluble or insoluble? It's insoluble. Okay, those are some hydroxides. Let's move on to the next. If it's not one of those, we'll we'll check. It's a sulfide. Sulfides, what's the formula for sulfide? SO. SO what? Automatically I would not think O because I have the wrong letter. O needs not a D, O needs a T. Right? O needs a T like thunder or something like that. It needs a T because of oxy. If it's a D, then that tells me most likely it is a monatomic or polyatomic. If it's a D, it tells me most likely it's monatomic, unless it's one of the strange ones. So what's the charge on sulfur? 2 minus. So that's 2 minus. Sulfides. These are insoluble, except for group 1 and ammonium and group 2. All right, so let's take a look at this one. Let's go with chromium 3 sulfide. What would the formula for chromium 3 sulfide be? CR2S3. CR2S3 is right. This solid, is it soluble or insoluble in water? This is insoluble. Okay, let's try sodium sulfide. What's the formula for sodium sulfide? Na2S. That would be sodium sulfide. Is it soluble or insoluble? Soluble is correct. Na2S is soluble. Some sulfide. The next anion we're going to look at will be the carbonates, chromates, and phosphates. This is not a comprehensive list. These are just some of the common ions, anions, cations that we encounter. If it's not one of these, typically we see, it might be similar to one of these, or we just look it up. And so when we're looking at the carbonates are what? What's the formula for carbonate? CO3, good. Charge? Minus. Chromate? CrO4, charge. Phosphate, PO3. Is Is it 3 oxygen or 4 oxygen? PO4. Charge? And so let's take a look at some of these. For example, here. Ammonium phosphate. What's the formula for ammonium phosphate?
NH4PO4.
NH4PO4? Is that right? Do the charges balance there? No, they don't. How can we get the charges balanced? Because NH4 has what charge?
3 minus.
Plus 1. Phosphate's 3 minus. And so how do we fix this? NH4, 3. We need 3 of the ammoniums to balance out the charge on the phosphate. So this would be ammonium phosphate. Ammonium phosphate, is it soluble or insoluble? It's soluble. But all ammonium salts are soluble, so we wouldn't have gotten this far. We would have stopped at step A for this particular one. Okay, we're going to go to this next one. Calcium carbonate. What's the formula for calcium carbonate? CaCO3, that's correct. This white solid, is it soluble or insoluble? It's soluble. Wait a minute. Is it soluble? I forgot to write. These are insoluble except for group 1 and ammonium. That's it. So if it's not group 1 or ammonium, then it's going to be insoluble. Well, this is not group 1 or ammonium, so therefore this is going to be insoluble. Insoluble. So we wouldn't expect it to dissolve. So we can get an idea, when we look at the solubility rules, there are different things we can do. One thing is we can step back and look, is there a pattern to the solubility rules, or is it just straight memorization? And it's okay if it's straight memorization, but eventually you want to start thinking, is there some kind of pattern in there, or is it totally random? No, it's not totally random. There is some sort of pattern. Do you kind of see a pattern in it? Maybe, maybe not at this point. The other thing we think about is, what causes something to be insoluble? What causes something to be insoluble is it coalesces into a lattice, crystal lattice. And what causes it to coalesce into a crystal lattice is these ions must like each other. These ions must like each other enough to come together to form a crystal lattice structure, an ionic lattice. And so these are all the things that form insoluble solids are all favorable ion combinations. So for example, this isn't as favorable. Ammonium phosphate isn't as favorable as something like calcium phosphate. If I had calcium, what is the formula for calcium phosphate? Let's write it here. Ca3PO4 2. That's correct. Each calcium is 2 plus. We got 3 of those. It's total of positive charge is 6. Each phosphate is minus 3. 2 of those. Total negative charge is minus 6. Plus 6 minus 6 balances out. Calcium phosphate is soluble or insoluble? Insoluble. And so when we have an ammonium paired up with phosphate, it forms a soluble salt. This salt can dissolve in water. However, when we have calcium paired up with phosphate, it's tough. It doesn't want to break apart. It doesn't want to dissolve in the water. And so this is what we call a favorable ion combination. This is not that favorable. The only way to get the ammoniums and phosphate to come out and form a solid is by evaporating all the water. You know, think about it. The only way to get it to form the solid salt is if you evaporate the water. As you evaporate the water, the ions are forced together. You know, the less water there is, the more they have to come together. And eventually, all the water is gone, and then they're forced to come together to form a solid, right? Otherwise, they stay away from each other. And so this is where we're going to get some ideas about this. Now, why is that? Well, there are some patterns to this. There are some reasons for this, and we'll probably look at those later. But for right now, it's just taking in some observations and then seeing. So the first point is that regardless of if there's a pattern or if there's no pattern, you need to memorize these rules. So however you can memorize them, that would be good. All right. So this is just one aspect of metathesis. We'll come back to metathesis again later. All right, let's take a look at acids and bases next. For acids and bases, we consult the chart. No need to memorize. But, you know, even though there's no need to memorize, that doesn't mean you don't need to know some aspects of that chart. The acid-base chart is posted in the back of our room. I don't know if you can see it, but it's back there on the wall. But we need to memorize the 7 common strong acids. We must memorize the 7 common strong acids. Here are the 7 common strong acids. Remember, the difference between these strong acids is the anion here. The cation's all the same. What is the cation? H plus. These are a little bit different. These are, we'll talk about this. There's something called acids. Acids are proton donors, and bases are proton acceptors. And so this is a chart that combines both into one. This is a chart based on strength. What's the strongest acid here? The strongest acid here is what, H2SO4? Is that the strongest? Well, it turns out no. This is based on the rank here. Let's see. The strongest acid is going to be this one at the top. What is that called? No, that's not hydrochloric acid. You know, which one's hydrochloric acid? You see it? HCl. This is hydrochloric acid here. This is called something else. What is the anion? Is the anion chlorate? Chlorate is ClO. Chlorate. First, let's figure out chlorate. Make sure we have chlorate right. Chlorate has how many oxygens? 3. So it's ClO3. So ClO3 is chlorate. Therefore, ClO4 is perchlorate. And so that's perchlorate. Now, what do we do with an 8? We make it an ic. And so this would be called perchloric acid. And so at the top of the chart is perchloric acid. This is the strongest acid on this chart. What makes perchloric acid such a great acid? What makes it a great acid is its ability to lose the cation. You know, when I talked about favorable ion combinations, it turns out H plus and ClO4 minus isn't that favorable. If H plus and ClO4 minus were a really favorable ion combination, then they're like a pair. They're stuck together, right? But what happens with HClO4 is this. HClO4 can easily lose that H plus and leave the ClO4 minus alone. And so ClO4 minus and H plus aren't a good pair, and therefore they split apart easily. That's it. So there's something called the conjugate relationship, which I'll talk about in a minute, and that is, this is a table of acids and bases, because if I go left to right, I'm donating proton or losing proton. If I go right to left, I go backwards here, then this is accepting proton. And so the conjugate relationship is this. This is a very strong acid. And therefore, its conjugate is very weak. This is a very weak base. Bases are proton acceptors. And so this one really doesn't want to accept that proton to go back to HClO4. This one wants to stay away, and therefore it's a very weak base. And these are conjugates of each other. So it's like a seesaw relationship. If one side is strong, the other side is weak. Vice versa. But we're not going to worry about that. We're just going to worry about naming the acid. So this is why I want to do this now, to get more practice naming and doing other stuff. So let's take a look at this. Below perchloric acid is what acid? HI. HI is called what's the anion? Anion is iodide, and so what do we do with an IDE ending? We use the hydro prefix and the ic acid. And so it would be hydroiodic acid. Hydroiodic acid, HI. Hydroiodic acid is number 2 on the chart here. It's strong acid. What's number 3? HBr, which is called hydrobromic acid. Below hydrobromic is hydrochloric. Below hydrochloric is sulfuric acid. Below sulfuric is hydrochloric acid is this one, HCl. This one's called perchloric acid is the top one here, HClO4. HClO3 is chloric acid. This is chloric acid, and then this is bottom one, nitric acid. So you aren't going to memorize the top 5, you're just going to memorize the top 7. You need the top 7 in any order. You don't have to memorize the order, but it's nice to know perchloric's at the top and nitric's at the bottom. talk about. This ion doesn't occur in compounds necessarily. This ion is found in water. And this ion is called hydronium, H3O+. Hydronium. And so you aren't going to find any salts like hydronium phosphate. You don't see that. You can see phosphoric acid. So hydronium is something that comes in water. So the acids above hydronium are strong acids. The acids below are weak acids. And so we don't want to memorize a whole bunch of stuff. So what we'll do is we'll memorize the 7 common strong acids. And then if we see another acid, we'll think it's not strong. It must be weak. So the acids go like this, down here. This acid's weird because, you know, what's a cation, what's an anion? It's hard to see, but this is written more like an organic chemist would write it. This is a condensed structural formula. The cation is H over here. The cation is written over here, but it doesn't matter in this type of molecule how you write it. This one's called trichloroacetic acid. Trichloroacetic acid is a pretty strong, weak acid. Right at the border. We got trichloroacetic acid followed by this one. I wouldn't have expected you to know the name, but this one I do expect you to know the name. What is this? This is an anion. It's got a negative charge, and it's an acid because it starts with an H. So this is an acid anion. The name of this acid anion is what's the name of the anion itself? SO4. What's that called, SO4? Persulfate or just sulfate? Sulfate. So SO4 2- is sulfate. We add an H plus to that, get an HSO4, and that is called hydrogen space sulfate. So we have the hydrogen sulfate ion. There's another name for hydrogen sulfate. It's called bisulfate. Bisulfate's a pretty decent acid, you know, even though it's an acid anion, it's pretty decent in terms of strength. So it's actually hydrogen sulfate or bisulfate's a stronger acid than this one. What is this one called? This one's called phosphoric acid. And so bisulfate ion is stronger acid than phosphoric acid. You don't have to memorize the orders to be able to name these. What's this one called? We're going to take a pass on this one. This one is acid they'll encounter in Chem 1b. Take Chem 1b. It's basically the iron 3 ion dissolved in water. Iron 3 ion dissolved in water is stronger acidic. It's a stronger acidity than this acid here. This acid is called what? So why don't you guys try to name these acids here, starting with HNO2 and working your way down. So spend a little bit of time working on these and getting the names for these down. Then I'll be right back.